1 to 1 equal to 0, because 1 is the destination. Distance to self is 0. And all other nodes is infinite, because initially we have no guess. We take the maximum possible. Then we do a loop, find a number of steps, where at every step of the loop, we do the following. We compute the minimum of what we had at the previous iteration. This is the estimate we have of the distance in the previous iteration. So we take this estimate plus the cost. So I am node I. I ask myself, how much would it cost me to go to node 1 if I pick as neighbor j? So if I pick j as a neighbor, the cost will be to go to this neighbor, plus the cost that this neighbor had computed in the previous iteration. So I don't know what the true final distance is, but I say everybody has an estimate from the previous iteration. I take this as the estimate, and I compute my new estimate by doing that. And I take the minimum over all those nodes. Here I say over all other nodes j, but of course, if aij is infinite, this term is infinite, so it will never be equal to the minimum. So in practice, that means we take only the neighbor vectors here. So we do that, and we hope it will converge. And convergence here simply means it becomes stationary. There will be one step in which the set of distances does not change here. If that happens, I return the step at which I have converged, and I declare that those are the distances. If that does not happen, the algorithm will run forever. It will not terminate here. This is Bellman-Ford's algorithm. So let's see an illustration of it to understand what it does. It's very simple. It's simpler than Dijkstra's algorithm. And we'll see it's even simpler also to interpret. I'm showing here a network, a toy network with 1, 2, 3, 4, 5 nodes, distances on the edges, which are the same in both directions, and the destination node of interest is node 1. All the other nodes are called with letters, B, C, D, E. Right. And I'm putting in the box here the estimates that we have of the distances to node 1 at every iteration of the algorithm. Here I'm talking of the centralized version of the algorithm, that is a hypothetical version of the algorithm that runs on a single processor here. What we will see is distance vector does not use this one. It uses a distributed version. But first, let's study the centralized version here. So we see that initially, the estimated distance at node B is infinite, because that's the initial condition everywhere, except at the final destination. Then at iteration 1, what happens? At iteration 1, B will compare all of its neighbors. So it has 4 neighbors, and it will compare what is the cost to the destination if I go to one of the neighbors. If I go via C, I have infinity plus 6, that gives infinity. If I go via E or D, is the same, but if I go via 1, the cost I have is 1 plus 0, which is 1. Therefore, when I run iteration 1, I find a final distance of, an estimated distance of 1. Similarly, D will talk to all of its neighbors. It will talk to 1, which gives a distance of 5. It will take what B has, which gives infinite, and E also infinite. So the best distance is 5 at iteration 1. This is the state here. C and E will not improve because C will compare to their neighbors that all have infinite distances, so they still are infinite, and E and 1 does not change. So this is what we will have at this point here. One interesting thing here is to think of what I've explained in a different way as message passing. Instead of saying, I do it centrally, let's assume that we have a first step towards distributing that. Assume that when B compares a thing, one way to do it is to ask each of its neighbors, what is your estimate today? So B could ask C, what is your estimate? C will say it's infinite. And similarly, so here, I'm talking of E. E asks its 3 neighbors, C, B, D, what is the information you have, and we'll give those 3 costs here. So that's another way of thinking of this system, but that's the way that's useful because this is how we can make it distributed. So we can think of this line of code, which is here, as saying, node I asks each of its neighbor j, what is your estimate? I add to your estimate the cost of going to u, and I compare all the results of all my neighbors. I take the best one. And that gives 3 here. And the synchronous, we can interpret centralized Bellman-Ford as being a synchronous message passing method. Synchronous means in one round k, we ask exactly all the neighbors what were the results in round k minus 1. That's a synchronous way of organizing a distributed system. What we will see next is that even if we relax this, if we make the thing completely asynchronous, we ask our neighbor, what is your last estimate, whether it's round k minus 1 or k minus 2 or k plus 1, doesn't matter. What is your best estimate so far? If we do this in this completely asynchronous mode, that will give us the true distributed Bellman-Ford algorithm here. But before getting there, we need to understand a number of the properties of Bellman-Ford here. So here, I'm showing iteration 2. So at iteration 2, we see that things have improved. Now, for example, C can ask B and E, what is your distance? E is not very interesting, infinite, but B gives a distance of 1. So in the next iteration, C will find a best distance of 7. B and D will not change their best distance. E similarly will learn from B that there is a distance 1, so it will set it to 3. So at iteration k equal 2, this is what we will have. If we continue this, so if we continue the boxes here, does it stop? And if it stops, when does it stop for this specific run of the algorithm? And the correct answer is D, k equal 4. Well, we can simply run the simulation. We see that k equal 3, we will obtain those values. C and E will improve their distances. And at k equal 4, it doesn't change. We can see a bit more. If we look at the solution here, why did it stop here? Well, we can interpret very simply what happens at every iteration of this algorithm. We can see that at iteration 1, the distances were 1 and 5 for B and D. It is, in fact, the distance if we can go to the destination in one hop. At iteration 2, that's the distance we have if we are allowed to use up to 2 hops. Right? So we see C had found a value of 7, which is the value it finds here. At the end, C will find a better path, but that's a path in 3 hops. It gives a distance of 4, but we'll find it at iteration 3. So that's one of the properties of this algorithm, the Bellman-Ford algorithm as I described it. At iteration k, it is very, very simple to show that in fact what it computes is the distance to the destination for a traveler that is allowed to take at most k hops. And of course, if the network is connected and finite, eventually it will converge to the shorter distance. And it will stop at k, which is the diameter of the network, or before. But the largest number of hops, which is at most k, so it will stop at some point, typically well before the number of nodes. Here it had stopped at k equal 4, which means at k equal 3, it had already found the correct value. Well, that is exactly the theorem that is very simple. So you see, it's much less sophisticated than Dijkstra. It's very easy, and that's a natural thing to do. This version of the algorithm computes exactly the shortest paths. But more specifically, we knew that the intermediate values at iteration k are the distance in at most k hops. And then there's another property, which is shown here, or here. After all, what we want is not, what we obtain is only the distances to destination. But what we want is not the distances. What do we want in a router? We want the next hop, where to go. Why does the distance give me the next hop? Well, the distance alone does not, but the distance and the distances of all my neighbors give me the next hop. So if I know not only that the distance from me to the final destination is 4, but if I know also that the distances from B and from E are 1 and 3, I can know which way I should go. And what is the method? Well, I test. I try to go via B. I know the distance from B to destination, it's 1. Plus me to B is 6, that gives 7. I know also the same thing for E. If I try E, I obtain 1 plus 3, 4. So by comparing all my neighbors, when the algorithm has converged, and finding which one gives the minimum also gives me which way to go. So in other words, whenever the algorithm has converged, if I look at what is the minimum of this expression over all neighbors, any j that achieves the minimum is also on the shortest path towards the destination. That's also a property of this algorithm. Which is then very powerful because it means by knowing my distance and the distance of my neighbors, which I know because in order to compute the algorithm, I've asked my neighbors what is their distances. So when the algorithm converges, I have all this information for free in some sense, and then I can know how to route here. So far, so good. However, there's a catch. In reality, things are never like I presented before. For doing things like I presented, we need to reset the network. We need to put the network into conditions where initially, at round 0, everybody has the values that I said. Which is not what happens if we want to have a fully distributed operation. What I would like is that every router sends to the neighbors their estimated value, and then the neighbors do this computation and send them again, and hopefully after some time it converges. But what happens if, due to some topology changes, a link breaks, a router disappears, the network changes? Then changing the network is equivalent to changing the initial conditions. So if I run this algorithm for some time and then I change the conditions, for example, I start from those initial conditions. For some reason, C, E, and D believe that they are at a distance of 1. Why is it? Perhaps because there was a direct link from them to 0, and this link has been broken. The 3 links at the same time were broken. They were using the same conduit, for example, that was broken. And B believes it is at the distance of 10, perhaps because the cost of this path has been changed from 1 to 10. So that is a very concrete and practical thing that might well happen. If we want to catch that, one way is to reset the network by discovering there is a change and then say, oh, you should not use those values, they corresponded to the previous things. How can we do the reset and how? That's the question. What will happen with this algorithm if we don't do a reset? If we say, okay, let me run exactly the algorithm that I've shown here, but the values are those ones. What is your best guess? What will happen? And then the majority, overwhelming majority, says C. The algorithm converges, but not to the correct distances. Well, I will not give you the solution now. Let's continue and see what happens. Let's do it, at least on this example here. If we do that at the end of the first step, so be a computer or a router for a few seconds, what is the result of your computation here? Well, the majority doesn't help us. Let's see what the truth is. So the value will be the ones that are shown here. So the correct answer, P1 of D at iteration 1 will be, P1 of D will be 2. So the correct answer is 2. If we see what happens is that this bizarre condition 10 will very quickly be lost because B knows by asking 1, and 1 is always the ground truth here, at least if we force P1 of 0 to be 0, then it will get the correct value. But what will happen to D? D speaks to E, and E says, I am at a distance of 1. Okay, therefore, D believes it is at a distance of 2. E will do the same thing. E will ask C and D, and both agree and give the answer of 2. That's what will happen at iteration 1. Then at iteration 2, they will continue this ping-pong game. They will say, oh, we are at a distance of 2, so each of them believes they are at a distance of 3. Right? So this ping-pong game is in the nature of the Bellman-Ford algorithm, and we'll see that it does happen in distance vector routing algorithms. And eventually, the same thing will happen here. C will do this ping-pong game, will increase to 4, but sooner or later, they will still compare to the distance by going via B, for example, here. E will compare via B, and it will no longer increase. It will not go beyond 4 because B has the correct value, and B will force E and D to have the correct value. And in fact, we see that at iteration 4 here, this algorithm converges. So at least in this case, it converges, and strange enough, it converges to the correct values here. Right. So let's ask another question. Let's assume we break those links here, all of those links, we break them together. And the network was in those conditions, which were the correct conditions of before, and then we continue running the algorithm. Now, of course, C will detect that B is no longer connected, so it will set the cost to infinity. You will detect it by BFD or hello protocols of some kinds. That's business as usual for any routing protocol. What will happen in this case? And the majority says that the algorithm does not converge, which is correct. Let's see in reality what will happen in this case. So we start from those conditions, then there will be this ping-pong game. C and E talk to each other, and they influence each other, and in every round they increase by 1 here. So 4, 5, 5, 6, 6, 7, 8, 7, etc. So this island will have the correct values, it has converged, but this one will, what we do call is counts to infinity. They will increase, and this will never stop. So the algorithm, of course, is not very good in this case. So it will do what we call counts to infinity. This happens in distance vector routing protocol, may happen. But observe that what the algorithm is computing is the true value, because the true value is infinite. The network is disconnected. The distance from C to 1 is infinity. And what this is computing is, in fact, the true value, which is infinity. The embarrassing thing is that it computes the true value, but in unbounded time. So we still need to catch and fix this problem. In very simple distance vector routing protocol, the problem is caught by such protocols like RIP work for small networks by putting the infinity to a small value. For example, in RIP, infinity is 16. Once you've reached the value of 16 here, you declare that the distance must be infinite because this is supposed to work in networks where the diameter is never equal to 16. So we have now the answer to our previous quiz. In this example, in these two examples, in fact, we found that whatever the initial conditions, Bellman-Ford converges, if it converges, to the correct solution. And if the correct solution is that the network is disconnected and the distance is infinite, then it will count to infinity. So in some sense, it's always doing the right thing, even when the initial conditions are completely pathological. So that is this result here that says if there is a path from a node to I, then for k large enough, it will stop at the true value for all nodes I. Right. Now, when doing that, we have lost the beautiful part that I mentioned half an hour ago, which is we could easily interpret what it is computing at step k, at round k, by saying this is the distance in at most k hops. Now, if the initial conditions are wrong, then this interpretation goes away. But by mathematical miracle, the algorithm continues to converge to the correct value. This is why Bellman-Ford can be used in a distributed way, because it is robust to any temporary bad conditions. If for whatever reason the values that one node has at one time are completely wrong, of course, if you change adversarially the values fast enough, that will not work. But if this is due to a failure or to a sudden change, and there is no further change for enough time for the algorithm to converge, then the algorithm will get back on its feet. This was synchronous Bellman-Ford. Now, in reality, we want to make it asynchronous. How can we do that? Here is a first version, which is not the one that is done in distance vector routing protocol. Therefore, I call it BF prelim, preliminary version. Well, the idea is very simple. Since all I need to do to run Bellman-Ford is to compare the minimum of the values of the neighbors and the cost of going to their neighbors, then the only thing I need to do is keep in memory the last values that all my neighbors have given to me. I remember all the previous messages. Then when I receive a new message, it replaces the previous message of this node. For the other nodes, I look at the one that I have stored, I compare, do the best. This is what BGP does with this rib-in. When BGP receives multiple routes, it keeps them in its rib-in database, and then it computes the best. So this is exactly the same thinking. And the result is that if we can assume that messages don't eventually all get lost, then this will converge to the true value, even if we've lost the concept of rounds. So if some nodes are very fast, and they do the computations very fast, and some nodes are very slow, or if the delay between some nodes is much more than between others, so it might be that a small fraction of nodes that can talk very fast to each other does many, many rounds, whereas other nodes that are to take more time to compute may take much more time, maybe at less advanced rounds. It doesn't matter. This asynchronous thing will not prevent the thing from working. This is related to the fact that we know that the initial conditions do not matter. So even if you move at a different pace, it will not matter here. So let's see an example here. Here I'm showing this distributed Bellman-Ford and the state that is kept by node E. Node E keeps its distance to the final destination, 4, and also it remembers the distance that have been advertised by all its neighbors. So C said 7, D said 3, B said 8. Then when B sends to E a new message with its new distance of 1, then what this node will do, it will compare now the new that I'm receiving, 1. I compare to the 3 that I have, 3 and 7. So if I go via B, via C, or via D, I know their estimates. I found what is the next best one. The next best one is in fact E, and that changes my value. I put it to 3. So this is exactly, like I mentioned, BGP does also to compute the new best route whenever it receives a new thing. Right? Let's assume we continue, and asynchronously, it will converge, right? Now, this version of Bellman-Ford is not very smart because it defeats the purpose of what we said before, although it's smarter than link state if you want, but it is a bit less smart in the sense that we still need state information, which is all a record of all what the neighbors said here. So if we're a purist, we want to even get rid of that, because the goal was to do something that just looks at the routing table and the cost to destination to solve the thing. So Homer proposed this algorithm, which he calls super duper, which simply says when I don't need to remember this, because the only thing I will do is I will compare whether something can improve. So all I need is to compare my own estimate, my distance to destination. Whenever a neighbor gives me a new value, I compare to this, which already encapsulates all the best information I had so far, and I compare this to what I would have if I go via this neighbor. If this neighbor did not change his mind, this will be the same as before. But if this becomes better, perhaps this gives me a better queue. So I would update it if it's the better thing here. So the only thing you compare is, so sorry, it's not the minimum, I should delete this, the over j neighbor is wrong. The only thing you compare is those two things, two numbers, the stored best estimate and the new one you would have tentatively if you go via this neighbor here. Now, if you do this, you don't need to store the Q of j. You just look at the one you have here. Does this work? And of course, we should be suspicious. If something is called super duper, then in general it's suspicious. So A is certainly not true. What is less clear is whether B or C is true. The correct answer happens to be B here. It's just B, but there is a but. If you look at this algorithm, it compares the estimate it has now to what it would have if the next one is better. So this algorithm can only decrease the value of Q of I. Right? It can only improve. So if you have an estimate now, whatever this algorithm does, this algorithm will never produce a value higher than the one we have now. So certainly, if the initial conditions are strange, or if there is a change in the algorithm, in the network, like we have seen before, a link is broken, so the true value has changed, then perhaps the estimate you have now, before the failure, is less than the true value. This algorithm will never be able to get to the true value because it can never increase. So the problem of this algorithm is that it can never increase. Now, if it turns out that the network is stable, there is no change during the whole execution of the algorithm, and if the initial values are the one we gave first, that is infinite for everyone who knows nothing, this will work. But in all other practical cases, we don't want to force us to be in this situation, because if there is any change, it will not work. So if we use an algorithm like this, we need another thing that will detect whether there is a change and sends a reset to everybody, which would be ugly, so we don't want this. So in practice, super duper is not a good idea. What instead is done in distance vector routing algorithms is this. Now the true version of the distributed Bellman-Ford algorithm is this one. You keep only your local estimate of the value of the distance to the destination, like with super duper. However, you do the following thing. You also keep not just this, but also, of course, you want to keep what is the next hop to the destination. So J is the next hop, which is the best you had found so far to go to the destination. We want to have that for the routing table. With Bellman-Ford, remember, we have it whenever we do an update. We think this new thing is better, then we say this neighbor is the next hop here. So we keep those information. And then when we receive from a neighbor its estimate Q of j, we do the following thing. If this neighbor is the one that we had as a next hop, no discussion, we update our estimate by the value of this guy plus the cost of going there. So if this guy was the next hop so far in my estimate, and if this guy changes its estimate of the destination, I accept it. Even if it's larger, I accept it, I don't compare to anything. This is the mechanism that will allow me to increase the cost. If one of the costs somewhere becomes larger, this larger will propagate to everybody here. Otherwise, if it is not the next hop, I compare whether what I receive is better. If it's worse, I don't take it. If it's better, I accept it here. Right? And if, due to this equation, I modify Q of I, which is typically due to the last condition, if the minimum is J is not the next hop, then I make it the next hop. So if the next hop sends me some information, I accept it. If someone else sends me some information and it's better, I accept it, and this guy becomes the next hop. Right? And so let's see an illustration here. I'm zooming on E. So E has distance 1 and next hop C, right? C has distance 1 and next hop here. So we are in a case here where we have abnormal initial conditions. Perhaps there was a direct link from C and E to 1, and this link has disappeared here. And assume now we continue the algorithm. Then what will happen? C will send the information to E, but because C was the next hop, E will adopt this information, and E will now declare that its distance is 2. And the next hop is still C. Right? So this will go on for some time, and you see that there will be a ping-pong game between C and E. E will also send the information to C, and then their distance will increase until they reach the value of 4. And when they reach the value of 4, because with this ping-pong game the values will increase, then sooner or later the other rules will come to play. For example, B sooner or later will send a message to E, and E will say B is not the next hop, so in order to be adopted it has to be better. But now because Q is larger, the next value will be better. So B will send this information, and Q will become 3, and the next hop will be B. And at the end, the algorithm will converge. So this is our last theorem in our series of Bellman-Ford variants. This version of Bellman-Ford converges to the true distances if the network is fully connected, and goes to infinity if there is no path from this node to the destination here. This is the correctness result. So we are almost to the end. We have seen the theoretical underpinnings of distance vector. It uses Bellman-Ford distributed, which allows to compute no distances to one destination, and the stored information is only the next hop to destination and the distance to destination here. We can interpret it as message passing, and we can really make work now as truly message passing, and it works even when initial conditions are not expected. But if the destination is unreachable, then the algorithm will count to infinity. Right here. This is what is done in protocols like RIP. RIP stands for routing. I don't remember what RIP stands for, but this is the prototype of the distance vector routing algorithm. And what's the difference between the theory and RIP? Well, one main difference is that we don't want to compute distances to one destination, but to all possible destinations. So when you use RIP, every router sends to their neighbors their estimates of the distance to all destinations, which is the value that they had stored in the routing table. This is why it's called distance vector. Every router sends to its neighbors its own vector of distances to all destinations. And using this, with the theory that we have seen a minute ago, all nodes are able to do two things. First, compute the correct distances, and from the correct distances, deduce also what is the next hop to a destination here. Right. And I think we will not go through the details because we don't have enough time to go through the details of this. So a few last words on RIP. So RIP is extremely simple in terms of code and memory. So this is why it was used for many, many years in routers. So we use RIP today essentially if we want to have something with a very small footprint. For example, if we want to run vector routing protocol between mobile phones, for example. So this is the minimalist routing protocol. It has a bad reputation in enterprise networks because of this counts to infinity problem. Whenever the thing is disconnected, to detect that it is disconnected, we need that nodes exchange messages that let them count to infinity, and we catch it by saying we reach a certain threshold, and this threshold is not realistic, therefore this must be infinite. But it may take some time. So the convergence to the true values when there are disconnections might be long, and that's one of the problems. There are optimizations of distance vector, most notably one by Cisco, which is, I would say, a serious competitor to OSPF that uses various optimizations. In particular, it doesn't use the distributed Bellman-Ford that we saw, but the prelim Bellman-Ford. So it keeps state information, which also remembers what the neighbors said before. If you allow more state information, you can avoid some of the count to infinity, for example. But this would be a longer story, and this we will not see in this lecture. Voilà, thank you very much, and see you tomorrow for the last test.